Hello everyone. I hope you're doing well and staying healthy. Today we are going to start talking about lab 2 of the class, which is called the Euler buckling lab or the buckling of columns. So for the lecture 1 of this series of lecture, we are going to go over the theory of buckling of columns or Euler buckling. This is for this specific class. You have seen this lecture before. We have gone over the Euler buckling in AESP 361, but for the future classes, they will not see the Euler buckling parts in the AESP 361. They will only see the Euler buckling analysis here, but what they will see is a very brief theory on shell buckling, and they will do analysis on shell buckling. They will do a visualization of shell buckling plus a DIC analysis. So the experiment they're going to do is a little more comprehensive than what you did last year. And if you are really interested in seeing the DIC analysis in shell buckling, I encourage you to join that lecture, that experiment. I can share the date and time with you, and you can always come and join. So the first lecture is going to be the theory. If you feel like you are caught up on theory, you essentially don't need to watch this lecture because this is pretty much the same thing we went over last fall, for most of you guys, for all of you guys, for most of you guys. It will be just a review of the theory we covered last year. This is essentially the same lecture as before, right? For the lecture 2, we are going to go over the experiments and the experimental device. What do we want to do in the experiment? What do we want to do with the experimental devices? And so on and so forth. And then we are going to have the experiment in, I think, in 10 days. Right? So not the Thursday, not September 3rd. It's going to be September 10th. Right? Yeah, your experiment is going to be on September 10th. We are going to perform these experiments in the Aerospace lab, which is in 300 Main Street. So let's start the first lecture. In the first lecture, we are going to talk about the stability and the importance of stability in mechanical design, in design in general. And we will also talk about columns. What does column mean? What do we mean when we say columns? What these columns refer to essentially, and then we will talk about the buckling failure and different important parameters in the buckling failure, like different types of supports and how do they lead to different equations to find the buckling load essentially. Okay, so in your previous lab, in the previous courses in general, we had two primary concerns as far as the mechanical testing was concerned. The first one was the strength of a structure, meaning its ability to support a specified load without experiencing excessive stress. Sorry. and the ability of the structure to support a specified load without undergoing unacceptable deformations, right? Now we are going to be concerned with the stability of the structures and also its ability to support a given load without experiencing a sudden change in its configuration. And the discussion in this semester is mainly focused on columns. We already know that the structures may fail in a variety of ways depending on their type, the condition of their support, which is a very important part of discussion in buckling failure, and the kind of load and the materials used in the construction of that structure, right? Failure can be prevented by designing structures so that the maximum stresses and minimum displacement remain within tolerable limits. Okay, and strength and stiffness are very important factors in designing a structure, as we have already discussed. The same ideas, the same principles apply to buckling failure. The buckling failure is different from a structural failure, but the same principle applies. We want to remain within the tolerable limit, so the buckling failure doesn't happen. And in order to do so, we have to make sure that we understand, or we can find what the tolerable limit is as far as the buckling is concerned. Okay, so let's see what a column is. What is our definition of a column? So your first and the most important part of a definition of a column in buckling analysis is that it has to be under compressive load. Okay, so that's part one. Whatever you're dealing with, whatever structure you're dealing with, has to be under compressive load. And then the second part is that its length must be an order of magnitude larger than the either of its dimensions. Okay, this type of structure is called a column. So again, a column is a beam, essentially, that is under compressive load, and its length is at least an order of magnitude larger than either of its dimensions. Okay. Due to the size of the column, the axial displacement is going to be very small compared to the lateral deflection. Okay. So in buckling analysis, the lateral deflection, because of the compressive load, is the primary concern for us, right? And we don't really care about the axial displacement. It's so small that we just neglect it. And this lateral displacement is called the buckling. Okay. Buckling of column can lead to sudden and dramatic failure. And it's actually one of the, I would say I don't want to say one of the most important failure modes, but it is one of the important failure modes. And as a result of that dramatic failure happening so many times, special attention must be given to the design of a column so that they can safely support the loads. In other words, so that they remain in tolerable. You get the idea, right? Tolerable limits. Okay, and buckling also, you just have to keep in mind that buckling is not limited to columns, but you already know that because we have seen a visualization of buckling of shells. But the analysis we are going to do is related to buckling of columns. Buckling can occur in many kinds of structures. It can take many forms. An example, a very common example of buckling failure, not buckling of a column, this case is a shell buckling, is when you step on an aluminum can. And I mean, you are stepping on an aluminum can will cause a failure in a structure. And in general, buckling is one of the major causes of failures in a structure. We have an example of a can that is stepped on and failed. So you can see that it has failed. It starts failing with the buckling, of course. Let's say this is your aluminum can. If you step on it, it will start doing this, something like this. It is actually shell buckling, so it will be something like this. And then the structure will fail. Okay. Very common columns are very common. As you can see an example of columns in this water tank here. And you just have to, as an engineer, you just have to make sure that you remain within tolerable limits. Tolerable limits. And you also a failure of an oil rig. It is obvious that the buckling has started from here, but it has actually caused the whole structure to fail. And this shows you how expensive the buckling failure, any kind of failure, can actually be, and how it is just very simple, better design, a more safer design, if you will. You could have prevented this buckling damage. Buckling is also very important in aircraft and in aerospace analysis in general. As I'm pretty sure you have seen, we have seen these videos before, but you should have seen other examples of buckling failure in aerospace industry. So what I'm gonna do here is I'm gonna show you these YouTube videos, but these are the videos this group has already watched. So let's go over them. Let's see what they show us. Okay, so in this video we are gonna see the wing buckling sequences on a Goodyear inflatoplane in a Langley full-scale wind tunnel. Goodyear is a company that makes tires, right? And wind velocity is 69 miles per hour, so angle of attack is negative 4.25. So you can see here, these are the wings, right? They are going through just regular flight, if you will. So I just want to make sure that you are seeing what is happening here. So because the force actually there's a force at the tip of the wing that is causing the buckling on the wing, and there's also a force at the leading edge, right? Both sides. So it is important to keep in mind that we will have a lot of moments operating on the wing and fuselage, and if we are not careful about them, you may actually design them to be safe as far as the yield goes, the yield stress goes, but they may not be safe. They may they may fail because of the buckling load, right? And we're going to see later on that the buckling failure happens earlier than the yield failure or other types of failure in general. Okay, we have another view of the buckling failure here. Okay, with higher frame rate, you can see it actually is being spelled. You also have to keep in mind that this is an inflatable plane, so your structure, your plane structure is gonna be a little more resilient to buckling. But you can see this is a very good representation of forces that are being applied on your plane. Okay, let's see the next one. And this next one is actually a very short video. Again, you have seen this before. There's 3 seconds. But two of the labs actually, your goal is gonna be design and analysis, something like design and analyze something like this, right? So we are going to ask you to use ANSYS or any other software, and we're going to teach you ANSYS, of course, to test the wing at different angles of attack and see whether it will buckle or not. Okay, and just do the buckling analysis. I do a numerical test of buckling analysis. Okay. Let's see the next YouTube video. So this is an example of shell buckling. Again, a plane buckling. So this is an example of plane buckling. I'm just gonna go forward a bit. You can see the buckling happening here, and here, and here, and here. The buckling is this is a different mode of buckling if you recall from our previous analysis. So when you're dealing with a plane, it's the same as the buckling of the can. The buckling will look like this. So it wouldn't be like the first mode of buckling that you have a column that is just has deflection in one direction. So it will look like this. And that was you saw that is what you saw in that YouTube video. Okay. So let's try to see if we can find the buckling load, if there's any way to find the buckling load. We consider this figure. So this is actually an arbitrary. This is an arbitrary or this is an assumption. This is I'm sorry. It is a hypothetical structure that is supposed to represent this type of load, this type of compressive load on a buckle. So we just assume that there's a pin in between that connects it to a spring, and it has two parts. That's the column itself. It's two rigid bars joined by a pin at the center, held in a vertical position by a spring. And it is analogous to the figure on the left, actually, not the right. So these two are analogous to each other. That's the point. Because they both have simple support at the end and are compressed by an axial load P. Okay, so what we want to do is we want to relate this deflection. It may deflect this way or this way, right, to the load. Okay. So you just have to keep in mind that in our modeling of the buckling phenomena, we are assuming that elasticity of the buckling model is concentrated in the spring. The real model can bend throughout its length. That's very important. But here in this model, the deflection is going to be concentrated in the spring. Okay. And two bars are assumed to be perfectly aligned. And load P is along the vertical axis. These are very important as far as the buckling of columns is concerned. And a spring is also on a stress. Bar is in direct compression. And based on that, we can assume that after you apply the load P, what's going to happen is that the spring is going to move a little bit and we're going to have the deflection delta. The deflection angle is very small, so essentially we can just find the deflection delta by multiplying the angle by the length here, right? It's a geometric relationship, it's a sinusoidal relationship, but since the theta is very small, we are just removing the sines and cosines and tangents. Okay? Sorry. Okay. And as I mentioned, a structure is disturbed by an external force that causes point A to move a very small distance laterally, right? And the rigid bodies rotate through a small angle theta, and there's a force developed in the spring, and direction of the force tends to return the structure to its original straight position. And this force in the spring is called the restoring force. At the same time, the tendency of the compressive force is to increase the lateral displacement. Okay? So we have two forces in the opposite directions. One of them is the displacing force, which in a real column is acted by the elasticity of the column, right? That is actually that the column wants to move back to its original position. But we also have the compressive load that wants to move the column, buckle the column even further, right? So restoring force tends to decrease the displacement, this displacement delta, and axial force tends to increase the displacement. Now what's going to happen if we remove the disturbing force? Okay, if your P, the load you have applied, is very small, the restoring force will dominate, okay, over the action of the axial force, and the structure will return to its initial straight position. Then we call that structure stable. Okay, if P is large, if your compressive load is large, the lateral displacement of A will increase, and the bars will rotate through the larger and larger angles until the structure collapses. Okay, then we call this structure is unstable, and the structure will fail by lateral buckling. Okay, the maximum load that a column can support when it is on the verge of buckling is called the critical load, P critical. And that's actually pretty important. This definition is pretty important because the critical load is a maximum load a column can support when it is on the verge of buckling, right? So that's actually the point where if you increase the point by just one very small epsilon, if you will, then the buckling failure will happen. And if you decrease the load by a small epsilon, the column will go back to its original position, okay, original configuration. But if you keep the load as P critical, the column will stay as is, doesn't change, doesn't fail, doesn't go back to its original position. And as long as P is smaller than the critical P, the critical load, your column is going to be stable. When P reaches the critical load, the column becomes unstable. which is actually when P passes becomes greater than the critical load, the column becomes unstable. And therefore, we actually can safely say that the P critical represents a case of a neutral equilibrium. Okay. Meaning that any small disturbance will cause buckling if that disturbance is increasing the force that is being applied. And generally, as I've mentioned earlier, your P critical is smaller than the yielding load. Again, this is very important when you're designing whatever, an aircraft or anything, right? Because if you design a structure for it not to yield, and the structure is exposed to a buckling or a compressive load, then it is very possible for a structure to buckle before before yielding, right? So you always have to be mindful of the buckling failure when you're designing something. So let's talk a little bit about the critical load and the stability of columns in general. The transition between stable and unstable conditions occur at the value that we have discussed before. It is a value of actual force called the critical load. We can find this critical load by considering the structure in the disturbed position and consider equilibrium, right? So we are assuming that the configuration of the structure has changed a bit, but it has uh, stayed in that configuration. It hasn't gone back, it hasn't failed. Okay. And then we can find the free body diagram and some of the forces in the x direction. X direction is this direction. We have the spring force F, and we also have the load multiplied by tangent of the buckling angle. And then, as we are still in the two rigid body system connected by a pin, so consider the upper bar as a free body subjected to an actual force P and a force F in the spring. The force in the spring is going to be equals to a stiffness of the spring times the displacement, the buckling displacement, delta. Okay, we can say F is equal to K multiplied by delta. And since theta is very small, the lateral displacement of point A, that delta is actually, as we have seen before, can be assumed to be theta L over 2. Okay, so we write the force balance 2 multiplied by P critical theta is gonna be K theta multiplied by L over 2. So your critical pressure, your critical load is gonna be equals to the stiffness of a spring multiplied by L over 4. So if you can find the stiffness of a spring, then you will be able to find the critical load. Okay, again, so what it means, the critical load means, is that if if the P you're applying is less than the critical load, which is the stiffness multiplied by L over 4, so we don't need to include that to do any force analysis anymore. We just can use this equation and find the critical load actually. Then your column is stable. This condition is called a stable equilibrium. We'll talk about this term a little more later on. If your P is larger than P critical, column is in unstable equilibrium. This means that the column will tend to move out of equilibrium and not to be restored to its original position, meaning that it will eventually fail. And if P is equal to P critical, column is in the neutral equilibrium. This means any small disturbance will cause buckling. Okay? And the load point P equals to P critical is called the bifurcation point. So we have unstable equilibrium, we have a stable equilibrium, and we have the neutral equilibrium, or the bifurcation points. At this value, the structure that at the P critical value, the structure is going to be in equilibrium regardless of the magnitude of the angle. And you have to keep in mind that we did all of this analysis assuming that the buckling angle in the column is very small. Okay. Critical load is the only load for which the structure will be in equilibrium in a disturbed position. Okay. So that is very important. So you can actually, if your load is at the critical load, your column will change its configuration, but it will not fail. Okay. At this value, at the critical load value, restoring effect of the moment in the spring matches the buckling effect of the actual load, representing the boundary between the stable and unstable conditions. Okay. If the actual load is less than P critical, the effect of moment in the spring dominates and the structure returns to the vertical position after a small disturbance, which is the stable condition. Okay. If the actual load is larger than P critical, the effect of the actual force predominates and the structure buckles, which is again called the unstable condition. So another representation of the same thing. So for the past 3 slides, we are essentially repeating what we have already stated about the stable, unstable, and neutral equilibrium, mainly because this is one of your most important concerns in buckling, and this is something that you have to be mindful of when in the lab, right? So we have different buckling points, load points. I'm sorry, and as you know, as we have seen, the boundary between stability and instability is called the neutral equilibrium. That load point actually is called the bifurcation point. Okay. This idea of stability is analogous to the very famous ball placed on a smooth surface. If the surface is concave, meaning that it is inside the dish, the equilibrium is stable, and the ball always returns to the low point when disturbed. If the surface is convex, like a dome, then the ball can theoretically be in equilibrium on the top surface. But the equilibrium is unstable and the ball will roll away. And if the surface is perfectly flat, the ball is in neutral equilibrium and it stays there placed. And you can see a representation of what I just said, or what I just read actually here. Okay. But before moving on, we have to represent the idea of an ideal column. So an ideal column is a column that has a very high critical load, right? So essentially, it is very hard for the ideal column to fail, meaning that we assume the buckling, or we can observe that the buckling failure happens because one of these conditions is not met in your column. So what are the conditions of an ideal column? It has to be perfectly straight, right? Which is obviously is not going to happen in the real world. The material that is used in constructing the column must be completely homogeneous, which again doesn't happen at all, okay, in the real world. And actually the other point that is one of the main points of an ideal column is the load must be applied through the centroid of the cross section. And also the material must behave in a linear elastic manner. So if it moves, if it changes its configuration, it will go back to its original configuration. And if that's the case, then your column will buckle or bend in a single plane, and it will always go back to its original position when you remove the load. Okay. So in looking at the columns under this type of loading, or the loadings that are assumed to be at the centroids, we are only going to, or under compressive loading at the centroid. We are going to look at three different types of supports, and so just keep in mind that this is the definition of ideal column, and what we meant here is that these are not really met in the real world. That's why we will have the buckling failure. That's what the load is actually can be higher than the critical buckling load. But let's go back to the analysis of the theory behind the critical buckling, or how can we find the actual buckling load that is going to happen. Yeah, and I mean we already have an equation that's the KL/4, but we don't have the spring stiffness there, right? We never have the spring stiffness because that is not a real spring, right? That was just an assumption, that was just a hypothetical structure to help us analyze the case. So we have to look at the critical buckling from another point of view. In looking at the columns under the compressive loads, we are only going to be focused on the three different types of supports, mainly these three: pin supported, doubly built in, and the free support, which will result in a cantilever beam. Okay. The first part of analysis is going to be working on the pin supported column because it is the easiest one to work with, and we can actually extend this analysis to the other types of columns, right? Again, as we have mentioned, due to its imperfections, no column is straight, so the critical load is going to be much lower than the ideal conditions, right? And at some critical compressive load, your column will definitely buckle. To determine the maximum compressive load, which is going to be our buckling load, we assume that the buckling has already occurred. Okay, so we are assuming the structure has already failed, right? Failed through buckling failure. Okay. So making the assumption, the first thing you need to do is to write the free body diagram for a section of the beam that is cut from the top, right? We have the compressive load at the top here, P, and if you just cut it from anywhere, you will have a moment M and a P that is going to apply. The deflection of the beam is going to be V, and this distance is going to be X, right? So the maximum distance you're going to get here is going to be L, and the maximum deflection you're going to get is going to be the delta, right? So X and V are two of the variables we have here. Okay, we can equate the moments. We can write the moments balance here. We can equate the moments at the cut end here and find the equation for it. M at each location X is going to be equal to negative this P multiplied by V, right? So it is going to be in the other direction. Okay. We already know that the deflection of the beam is related with its bending moment distribution, right? And we can see that here as well. So we can write this equation that we have seen many times in bending analysis. EI multiplied by the second derivative of the deflection in this direction, or with respect to deflection in the X direction, is going to be equal to your moment and your moment is negative P multiplied by V. And we can actually rearrange this equation. We can move the EI to the other side and move the whole thing to the left to get this differential equation. D squared of V over dx squared plus P over EI multiplied by V is equals to 0. This is a form of a second order differential equation of this type. D squared V over dx squared plus alpha squared V is equals to 0. This is one of the very famous or common ordinary differential, the second order differential equations that we can see, and we already have the solutions for it. So the solution is going to be looking like this. And keep in mind that your alpha squared is actually equals to P over EI. The assumption we are making here is that P, E, and I are constant. It doesn't change. So this is just a constant as multiplied by V. Right? So your final solution is going to be of the form of V equals to A cosine of alpha x plus B sine of alpha x. In order to find A and B, we have to apply the boundary condition. We are dealing with the partial differential equation analysis. Okay. We can write the boundary condition as x equals to 0, which is talking about, let's cut up the beam. X equals to 0. This is x equals to 0. Your V is 0, right? And at x equals to L, your V is also going to be 0, right? So from the first boundary condition, we can conclude that A is 0. Very simply, just rewrite this equation. Let's do this. A cosine of alpha x plus B sine of alpha x, right? You plug in x0 here. Sine of 0 is 0, right? So this term will be 0. It doesn't matter what V is, okay? And V is 0, so A cosine of alpha x is 0. Cosine of alpha multiplied by 0 is 1. So 1 multiplied by A is 0, which means that your A must be always 0. Okay. Then using the next boundary condition, we eventually get to this term. Your V is 0 and x is equals to L, right? We can have two solutions to this. Either B is 0 or sine of alpha L is 0. This cannot happen because if B is 0, it means that your V is always 0, which contradicts the assumption we already have. We assume before starting the analysis, the main assumption was that buckling has already happened. So this cannot be true, B cannot be 0, and this will become true. Sine of alpha L is 0. Sine of alpha L is going to be always 0 for alpha L equals to 0, alpha L equals to pi, alpha L equals to 2 pi, 3 pi, and you can conclude that for alpha L is equals to n pi, sine of alpha L is going to be 0. Okay? So this is actually going to be our solution, right? We already know that we can actually take this to the power 2 alpha second L. Let me take alpha to the other L to the other side, and pi over L squared, and alpha squared is P over EI, right? Is equals to n pi over L squared. Okay. So the buckling load is going to be equals to n squared P squared EI over L squared, which means that we are going to have different buckling modes of buckling, because this n can be 1, 2, 3, 4, 5, 6. So we can have infinite number of modes of buckling. And the buckling, you can see a representation of different modes of buckling. So your first buckling is just a regular column buckling, and then we move on like this. It is obvious from the equations that P1 is smaller than P2, that is smaller than P3 for the same column with the same material and same everything. And if the column buckles at P1, it will never get to P2 or P3 unless we have some sort of a support mechanism in place that prevents the first mode of buckling to happen, right? And so for the first mode of buckling, your V is going to be 0, right? That is when you can get to second modes of buckling. And what kind of bracing we can have? We can actually, that's pretty simple. Let's go back here. Let's say, I wish I could show this to you in a class, but let's say this is the column. You just hold on to the middle of it with your fingers, right? It won't move, right? So with P1, nothing will happen. It won't buckle. But if you increase the compressive load, it can buckle from here and here, right? So if you have bracing in place, some sort of bracing, you can get to other modes of buckling of columns, right? So we started this analysis with assuming that we are dealing with a pin-ended column. So for that type of column, your critical load is going to be equals to pi squared EI over L squared. If your load is lower than the critical load, this load, you are safe and the buckling failure will not happen. If your load is higher than this, your buckling failure will happen, and this is the neutral equilibrium itself. This is called the Euler buckling load because it was the buckling was first mentioned by Euler, Leonard Euler. Pretty sure you're familiar with Euler at this point. Yeah. So let's start the class at this page. Let's stop the class at this page. We are going to continue the discussions about the axis of buckling and buckling in other types of supports later on. Let's see. Yeah, we're at 48 minutes, but so yeah, we are going to stop here, and we are going to continue this discussion in the next lecture, which hopefully I will upload as soon as possible. Okay, see you guys later, either in the propulsion class or in the lab, and stay safe.